So today we're going to be talking about the history of chemistry. We're going to look a little bit at the scientists who kind of started chemistry and also some of the early models of the atom. Again, most of this is review from last year. So just some of the early history of chemistry. It all started with the Greeks. There was guys called Democritus and Leucippus, and I believe Democritus was a student of Leucippus. And they kind of came up with an idea that was contradictory to the idea of the time. They thought that matter or all things could be broken down into smaller and smaller pieces, and that those pieces would always have the same properties of the larger piece of matter. They called this atomos, which is where we get the word atoms from. The trouble with their idea was that they didn't really have any experiments that were able to prove what they were thinking. And unfortunately, their idea wasn't that popular at the time. So not much else happened for the next 2,000 years in terms of chemistry and figuring out what atoms are. So about 2,000 years later, there was a guy named Robert Boyle. This was in the 1600s. Boyle became the first chemist to actually perform quantitative experiments. Remember, quantitative means numbers, measuring units, things like that. Before that, it was mostly qualitative, just describing what they saw. The thing he studied was the relationship between volume and pressure. And he, using this study that he did, he was able to develop a new definition of the word element. He said that an element is a substance that cannot be broken down into two or more simpler substances. And there he is. Next came Antoine Lavoisier. He was in the 1700s. He was a French chemist. As we learned last year, he studied combustion reactions and was able to determine that oxygen was an element and that oxygen must be present in order for anything to burn. But he also found that for any reaction, mass can never be created nor destroyed. He called this the law of conservation of mass. And this is something that carries over into all of the things we do in chemistry today, with things like balancing equations to show that you can't just create atoms out of nothing. They don't disappear. They can just be rearranged. So Joseph Proust was in the 1800s. He did experiments that showed that if you have a given compound, it always contains the same proportion or ratio of elements. So, H2O will always have twice the number of hydrogens as it has of oxygens. Now, they didn't know the chemical formulas necessarily for everything during this time, but he was looking more at the mass of the elements, and he was able to see that those ratios of the masses were always the same for any compound. This is called the law of definite proportions, this idea that in a compound, the elements always have the same ratio. So Dalton took this idea and said that if the masses are always in the same ratio, then the number of atoms should also be in the same ratio every time. So he was looking at different compounds, but basically what he said is that you can look at 1 gram of one of the elements, and each compound would have a constant ratio to that other element. So like in compound 1, there is 1.33 grams of oxygen that combines with 1 gram of carbon. in compound 2, there's 2.66 grams of oxygen that combines with 1 gram of carbon. So this shows us that the masses have this ratio, right? But what Dalton is saying is that not only do the masses have this constant ratio, but there's also a ratio between atoms. So the number of oxygen atoms and carbon atoms has a specific ratio in compound 1 and in compound 2. And those are properties of those compounds that cannot be changed. So he said that, like, in different compounds, when you see a different mass of oxygen in that ratio, that the reason for that is the difference in the number of atoms. So for example, in that chart, compound 1 could be carbon monoxide, 1 carbon to 1 oxygen, while compound 2 could be carbon dioxide, 1 carbon to 2 oxygens. And if we go back there, we can see compound 2 had double the mass of oxygen as compound 1, so that would make sense. He called this the law of multiple proportions. So when you have two elements that form a series of compounds, the ratios of the masses can always be reduced to small whole numbers, just like we can reduce this data to CO and CO2, a 1-to-1 ratio and a 1-to-2 ratio. In this example, we're going to be looking at the law of multiple proportions. So we have data for 3 different compounds that contain only nitrogen and oxygen, and we want to prove that it follows the law of multiple proportions. So in the table, we're given how much nitrogen combines with 1 gram of oxygen. So what we need to do is compare those masses of nitrogen for each compound to each other to see that it comes out to whole number ratios. So we're going to do compound 1 to compound 2. In compound 1, we had 1.750 grams of nitrogen, and in compound 2, we had 0.8750. When we divide those, we get 2, or 2 to 1. So we have whole number ratio. We can also do C2 to C3. Compound 2 to compound 3. So compound 2 was 0.8750 grams, and compound 3 was 0.4375. Again, we just divide those. And again, we get a 2 to 1 ratio. So again, 2 whole numbers. These don't have to be the same as each other, they just have to be whole numbers. Lastly, we can do compound 1 to compound 3. That would be our last combination. And when we divide that, we get a 4 to 1 ratio, which again is whole numbers. And so we can see that all of these ratios work out to simplified whole number ratios. So this does prove the law of multiple proportions. So Dalton came up with atomic theory, and this was kind of the first systemization of this idea of atoms. He took some of his ideas from what the Greeks had said and some from the experiments that had been done since then. So first is that each element is made up of tiny particles called atoms, which again is what Democritus and Leucippus were trying to prove. He also said that all atoms of a given element are identical. We know now that that's not necessarily true because we could have things like ions or isotopes where an atom has a different number of electrons or a different number of neutrons. But Dalton didn't know about protons, neutrons, and electrons at that time. The third part is that atoms are not created or destroyed in chemical reactions. They can be dissociated, combined, or recombined, so they can change what they're bonded to, how they're combined together, but they cannot be made out of nothing, and they cannot just disappear. And that's kind of what Lavoisier was getting at. And fourth, the compounds are formed when atoms of different elements combine with one another. And if you have a compound, it will always contain the same ratio and the same types of atoms. In order for it to be carbon dioxide, it always has to have 1 carbon and 2 oxygen atoms. Dalton also made the first table of atomic masses, which kind of leads into later into periodic table stuff, but it also helped to kind of show his ideas from the law of multiple proportions that showed those different ratios. One of the troubles with his table was that he assumed that nature would always be as simple as possible. So in 1809, a French chemist named Joseph Gay-Lussac did experiments involving different gases. He was reacting them under a constant temperature and a constant pressure. What he found was that 2 volumes of hydrogen, like maybe 2 liters of hydrogen, react with 1 liter of oxygen to form 2 liters of water vapor. Or maybe 1 liter of hydrogen reacts with 1 liter of chlorine to make 2 liters of HCl. So now, instead of just looking at those ratios within a compound, they're looking at ratios within a reaction. So you can see here the volumes in this picture show us kind of an example of that. So then Amedeo Avogadro came along, same guy who gives us Avogadro's number. A few years later, he kind of interpreted these results. He said, at the same temperature and pressure, equal volumes of different gases contain the same number of particles. So instead of just looking at the fact that it's 1 liter to 2 liters, he's kind of breaking it down like John Dalton did and saying, okay, those liters actually represent the number of atoms or molecules that we're dealing with. So before, when we said that 2 volumes of hydrogen plus 1 volume of oxygen makes 2 volumes of water, Avogadro was saying that really means that 2 molecules of hydrogen plus 1 molecule of oxygen will give us 2 molecules of water. Avogadro also assumed that these were diatomic molecules, which was kind of a new assumption. As I said, Dalton didn't really think about that possibility. So Avogadro assumed that things like hydrogen, oxygen, and chlorine were diatomic, which we now know is true. They are H2O2 and Cl2, part of the Brinkelhoff group of elements. So he was able to create an equation that we know now is the correct equation for this reaction of hydrogen and oxygen to form water. And these ratios given are the mole ratios, right? We can see that 2 moles of hydrogen reacts with 1 mole of oxygen to make 2 moles of water. He was saying that represents the number of molecules. And that also relates to, for these gases, relates to the volume. If we're looking at equal volumes at constant temperature and pressure. All right, so these were all people who were kind of helping to develop chemistry at the time. We also need to look at the history of how we came up with the model of the atom that we currently use. So we all remember J.J. Thomson. He was the one who did the cathode ray experiment. So this was in the late 1800s, early 1900s. He was studying electrical charges in cathode ray tubes. And he found that when he applied a high voltage to the tube, it made these negatively charged particles. And what he discovered was that those negatively charged particles were a part of the atom. Those are now what we call electrons. He took this one step further and was able to measure the charge to mass ratio of the electron. So basically how much charge per gram, although it wasn't really grams because electrons are really small. He assumed that all atoms must contain electrons, but atoms are neutral. They don't have an overall charge unless they're an ion. But for now, we're looking at neutral atoms. And so he decided that atoms must also have some kind of positive charge. And this led him to develop the plum pudding model of the atom. So this is our plum pudding model. So this gray area in the background is the positive charge. And Thomson said that this was just kind of spread out. Like the whole thing is positive, but it's like loosely positive, right? It's just all kind of spread out in there. And then these negative charges are the electrons. And he said those were just kind of randomly placed in this sphere of positive charge. So this is three-dimensional. It's like a big sphere, and these electrons are just kind of floating around in there wherever they want to be within this positive charge. So in 1909, a little bit after Thomson discovered electrons, Robert Millikan did an experiment with oil. He was doing oil drops, and he was actually able to calculate the mass of a single electron. So Thomson discovered how much charge per mass, but he didn't really figure out how big an electron was. Millikan figured out that an individual electron is 9.11 times 10 to the negative 31st kilograms. For comparison's sake, a single hydrogen atom, the smallest atom, is 1.674 times 10 to the negative 27th kilograms. So that's really small, but it's still a lot bigger than the electron. If we're looking at a human cell, that is about 10 to the negative 12th kilograms. So much, much bigger than an electron. All right, so shortly after Thomson came up with the plum pudding model, Ernest Rutherford was trying to test it. And he was going into this assuming that Thomson's model was correct. He created something called the gold foil experiment. So basically, in the gold foil experiment, Rutherford had this thin sheet of gold foil, and he had this detector set up going all the way around it. And he took this alpha particle and shot it at the gold foil. An alpha particle is a particle with a charge of positive 2. So it has a big positive charge, and he was shooting those at the gold foil. And what he expected to happen was for all of those positive charges to just go straight through the gold foil. Because the positive charge in the plum pudding model is so spread out, it shouldn't have blocked the alpha particles at all. It should just go right through. But what he found was that a lot of the alpha particles went straight through, but some of them were bounced off in weird directions, and some of them even reflected right back to where they came from, which Rutherford described as if you shot a bowling ball at a sheet of paper and it bounced back at you. So he was really surprised at this. So what he figured was that instead of that positive charge being spread out in a large space, it's actually condensed down into a really small space. And that makes it so that the positively charged alpha particle was reflected off of that other positively charged piece in the middle of these atoms. He called this the nucleus. So the nucleus is in the center of the atom. It has a positive charge and it's really dense. And all those electrons are still moving around it, but they're in this empty space that goes around the nucleus. So we now know that atoms all have protons, neutrons, and electrons. We know that the protons and neutrons are found packed into the nucleus, and they are what give the atom most of its mass. So you can see here, protons and neutrons are about the same mass. Neutrons are a little bit heavier, but they have way more mass than an electron. So they're found in the nucleus and give the atom most of its mass. The proton tells us which type of atom we're dealing with. So however many protons we have, we can look that up on the periodic table and see which element we're looking at. Protons have a charge of +1. Neutrons have no charge. The electrons are the smallest. They're the ones going around the nucleus in that empty space. They have a -1 charge. They don't really contribute at all to the mass. So if we lose an electron, we don't really notice a change in mass in the atom. But it does change the properties of that atom. And the electrons are basically what the atom relies on to do any type of bonding. And so if you recall from last year, we can lose, gain, or share electrons in order to form bonds to get a full octet. So the electrons are responsible for making compounds and making ions. The total charge of an atom is 0 if that atom is neutral. So if we're looking at a neutral atom, there will always be equal numbers of protons and electrons. And unless you're told otherwise, you should just assume that the atom is neutral. If we have a charge on that atom, we call it an ion, and then we can look at the difference in the number of protons and electrons. Sometimes you can have two atoms with the same number of protons, but they have a different number of neutrons, and that's what we call an isotope. So if the atoms have the same protons, it means they're the same element, but they may or may not have the same number of neutrons. So if you recall, we have some terms that tell us the different properties. The atomic number is the number of protons in an atom. The mass number is the protons plus the neutrons. And we can find the atomic number on the periodic table. It is the one that's written above this symbol. We do not find the mass number on the periodic table, however, because there are different isotopes. And so we would have to list all of the mass numbers for all of those isotopes, which would take up a lot of space and be pretty confusing. And so instead, the number that we see at the bottom is the average atomic mass, which is the average of all the isotopes of a given element. In this example, we're asked to find how many protons, neutrons, and electrons are in this atom. And so first, we can figure out which atom this is by looking at the symbol. Na is sodium. So we're going to be looking at sodium here. We can also look at this symbol and figure out a few pieces of it. So we know that this up here is the charge. Down at the bottom left, we have the atomic number. At the top, we have the mass number. So in order to find out how many protons there are, we just look at the atomic number because the atomic number is equal to the number of protons. So there are 11 protons in this atom. To find the number of neutrons, we'll need to look at the mass number because mass number is protons plus neutrons. And so to find neutrons, we're going to do 23 minus 11 because we had 11 protons. So remember, protons plus neutrons equals mass number, which in this case is 23. We had 11 protons, and so we can subtract to find that. So there's going to be 12 neutrons. Lastly, we need to find our electrons. To do that, we look at the charge. The charge is the difference between the protons and the electrons. To find the charge, we can do protons minus electrons. In this case, our charge is plus, so that's like a +1. If there's no number listed, it's just a 1. So we know we have 11 protons. So we have to think 11 minus what equals 1? Well, it would just be 1 less than 11, so that means there are 10 electrons. What is the symbol for an atom with atomic number of 9, mass number of 19, and charge of 1 minus? How many protons, neutrons, and electrons are there? All right, so to find the symbol, we first need to figure out which element we're dealing with. And to find that, we look at the atomic number. So we find atomic number 9 on our periodic table, which we see is F, fluorine. So then we know that the atomic number goes at the bottom left. The mass number goes at the top left. And the charge goes at the top right. So there's our symbol. We also need to figure out how many protons, neutrons, and electrons there are. So again, the atomic number is equal to the number of protons. So that means we have 9 of those. To find neutrons, we look at the mass number and subtract the number of protons because mass number is protons plus neutrons. So we see that we have 10. 19 minus 9 is 10 neutrons. And for electrons, we have to look at the charge. Remember, charge is protons minus electrons. In this case, our charge is -1, and our number of protons was 9. So we have to ask ourselves, 9 minus what equals -1? Well, 9 minus 10 equals -1, so we have 10 electrons.